Okay, so it's welcome to have Dominic Joyce, who will be speaking about vertex algebra and Lie algebra structures on the homology of moduli spaces. So please, Dominic.
Okay, thank you. So I'm going to tell you a story which I suppose is part of geometric representation theory, really. It's a way which appears to be new, or of defining some rather complicated algebraic structures on the homology of certain moduli spaces, primarily in algebraic geometry, although there are parallel constructions where you make algebraic structures on the homology of moduli spaces of connections in differential geometry. You can see, so this archive paper 2111 is a kind of huge, long paper, and there's also material in the previous thing, and there's documents on this in my webpage. So firstly, vertex algebras, they're really complicated algebraic structures which arise from conformal field theory in physics. They also occur in moonshine and in other areas of representation theory. All interesting vertex algebras turn out to be infinite dimensional. So I'm going to explain a new construction of vertex algebra, in fact, graded vertex algebra structures on the homology H star of M of certain moduli stacks M. So this construction is turns out to be extraordinarily general. And broadly, anytime you give me a reasonably nice additive category, such as an abelian or a derived category coming from geometry or representation theory, then I should be able to tell you how to define a natural vertex algebra structure on the homology of its moduli stack. So there's versions of this in algebraic geometry, in differential geometry, using topological stacks, and in representation theory. There's also a well-known functor from graded vertex algebras, V, to graded Lie algebras. And in my setting, this has a topological interpretation. So basically, the Lie algebra, which you construct from the homology of the vertex algebra by taking a quotient, turns out to be more or less the homology of a slightly different stack, the associated projective linear moduli stack, which is a kind of stack group quotient of the original moduli stack by the stack BGM. So this gives us a parallel new construction of infinite dimensional Lie algebras and graded Lie algebras on the homology moduli stacks. And the way I came to this subject was that I was studying wall-crossing formulae for enumerative invariance in various algebraic geometry problems. And it turns out that the wall-crossing formula of these invariants, well, the invariants really live in the homology of this projective linear moduli stack, and then their wall-crossing formulae have to be written in terms of a Lie bracket on this moduli stack. And it was finding out how to define this Lie bracket, which led me, in fact, to the vertex algebra theory as well. Okay, so I'm just going to flash up the definition of vertex algebra. So if you don't already know what a vertex algebra is, you're probably not going to get any wiser by looking at this, but you can at least get a sense of the kind of complexity of it. So R is a commutative ring, such as the rationals, for example. A vertex algebra over R is an R module V, simply a vector space, with a bunch of morphisms dn for n is 0, 1, 2, d0 is the identity. And then for each little v and big V, we get a linear map, Vn going from V into V, which is, there's also an identity element called the identity or the vacuum vector, satisfying a bunch of conditions. So roughly speaking, these operations Vn, they're like Lie brackets. So UN of V is kind of like a Lie bracket operation on U and V. And this is something like a Jacobi identity, although it's rather more complicated than that. These operations D, they're kind of like derivations. Yeah, okay, so these are, it's rather difficult to absorb what this is saying. But broadly, you've got an infinite number of Lie bracket-like operations which satisfy an infinite number of complicated identities. There's also graded versions of these, graded over the integers, and super versions of these where you have to change some signs. Okay, so it's usual to encode these maps UN for n in Z in a generating function form as our linear maps y of u comma z mapping from V into V of power expanded by power series in Z. So we write it like this. So we end up, we can recover the UN operations by taking residues. And then these y of u comma z, they're called fields, and they have a meaning in physics. And then you can rewrite your defining identities in terms of properties of these fields. One interesting property turns out to be this, that these operations y commute up to multiplying by some power of y minus z, where little y and little z are the operators of the formal variables you're sticking in these power series. So essentially, you've got some kind of rational function r of y comma z with poles at different places, such that the left-hand side of one, it's a kind of Lorentz series converging to this when mod y is less than mod z, and the right-hand side is a Lorentz series converging to this when mod z is less than mod y. So you can think about this as a kind of multiplication on V, depending upon some complex variable z, which has poles at z equals 0. And then under that interpretation, V is roughly a commutative associative algebra under this multiplication, and with a multiplication depending upon a formal variable with identity 1, but except the formal power series and the poles really make everything more complicated. Okay, so any commutative algebra with a derivation D gives you a vertex algebra such that y of u comma zv is just e to the zd of u times 1. I suppose my ring needs to include the rationals here. And that such things are, so you get, there's no z inverses here, so there are no poles. And such things are called a commutative vertex algebra. Any vertex algebra which isn't commutative is automatically infinite dimensional. So therefore, even the simplest non-trivial examples of vertex algebras are really big, complicated algebras, and they're difficult to write down. An important class of vertex algebras is called vertex operator algebras. These have a special conformal element, omega and v, and a central charge in your ring, such that if you write ln is the operation omega n plus 1, then the ln define an action of the Virasoro algebra. This is a special infinite dimensional Lie algebra appearing in physics, with central charge Cv. And L minus 1 is the first of your derivation operators. So vertex operator algebras are important in physics. I'm going to give a geometric construction of vertex algebras. Often they're not actually vertex operator algebras. Okay. If you have a vertex algebra, possibly graded vertex algebra or a super vertex algebra, and you take the quotient of V by the ideal generated by all of these derivations dk, this turns out to be a Lie algebra, and the Lie bracket is given by the operation U0 V mod D. So vertex algebras were introduced in mathematics by Borcherds. You notice that certain infinite dimensional algebras, which are important in representation theory, were constructed in this way. For example, Cox-Moody Lie algebras, they're kind of generalizations of ordinary kind of ADE Lie algebras. They're, in fact, Lie subalgebras of the Lie algebras associated to lattice vertex algebras. Vertex algebras also come from representation theory, both in representation of certain infinite dimensional algebras and in moonshine. So the monster group, the very large finite simple group, you can characterize it in possibly the most simple way as the symmetry group of the certain infinite dimensional vertex algebra. Okay, now let me move on to this construction I want to tell you about. So if A is a C-linear, abelian, or triangulated category from algebraic geometry or representation theory, for example, it could be the coherent sheaves on some smooth projective scheme X, or the derived category of coherent sheaves, or it could be the representations of a quiver, or the derived category of that category. So I'm now going to write M for the moduli stack of objects in this category A. This is something called an artan stack in the abelian case, something called a higher stack in the triangulated case. So what I'm doing, so stacks are a kind of space in algebraic geometry. They're more complicated than schemes and they have more structure. And this story I'm telling you is intrinsically stacky. If you try to do it with coarse moduli schemes, it just wouldn't work. So one of the things you probably ought to know about stacks is that as part of the structure of a stack, every point has a group attached to it, which if your stack is a moduli space of objects, then the isotropy group of each point is really the automorphism group of that point. So when you take a moduli stack of objects, the stack itself remembers the automorphism groups of the objects in your moduli problem. Now, when we form the so, for example, a simple example of a stack would be a point mod G, where G is some algebraic group, such as GLN, C. And that's a single point with a group attached, the group GLNC. So when you take the homology of a stack, the isotropy groups contribute to those homology groups. So, for example, the homology of point mod GLNC is actually the homology of the classifying space of GLNC in the kind of usual theory of topology and characteristic classes and so on. When we take homology of our moduli stacks, it's very important that that homology kind of automatically is kind of giving you contributions from the classifying space of the isotropy groups of the points in your stack. Okay, so when we given a bit of extra data on our moduli stack M, we're going to define a graded vertex algebra structure on the rational homology H star of M. Actually, this works on for other essentially arbitrary rings R, but commutative rings, but let's do it over rationals. We're also going to define a gradedly bracket on either a quotient of M by the translation operator D of that, or on the rational homology of a slightly different stack, a modification, in which we take our stack M and we quotient out by the action of the group stack point mod GM. This then makes this homology into a graded Lie algebra or a graded Lie superalgebra with, in fact, a non-standard grading. We have to shift the grading a little bit. Okay, we need a little bit of extra data. A perfect complex theta on M cross M, you can think about this as a kind of generalization of a vector bundle, if you like, satisfying some assumptions. So then the formulae for the vertex and the Lie algebra structures are going to involve the rank of this complex and its Chern classes. We're also going to need certain signs which are related to a kind of orientation problem for our category A, or essentially some kind of orientations on our moduli spaces. In order to make the Lie bracket we're going to construct antisymmetric, or graded antisymmetric, we need this complex theta to have a symmetry. If sigma is the operation, the morphism which just exchanges these two factors of m, then what I want is that the pullback under this swapping morphism of theta should be equal to the, or isomorphic to the dual of theta under some even shift. The m here doesn't really matter very much. What matters is that this forces the Chern classes of my complex theta to satisfy Ci of the pullback under the swap is -1 to the I of Ci of theta. Okay, so in essentially all of the examples we care about, there is a natural perfect complex, the X complex on M cross M, such that if you take the cohomology of this X complex at a point E comma F, you just get the X groups X to the I of E comma F in here. Now, if A is an even Calabi-Yau category, such as the coherent sheaves on a Calabi-Yau n-fold, Calabi-Yau 2 n-fold, for example, then by their duality, it's natural that you pull back, well, essentially this thing holds, and we can take theta to be the dual of the X complex. Otherwise, we take symmetrizations. We take theta to be the dual of the X complex plus the pullback of the X complex shifted by 2n, and then this is just automatic. So our examples are going to split into even Calabi-Yau examples and general examples, and actually the applications to enumerative invariance also split into even Calabi-Yau examples and general examples, because there's basically two ways of forming virtual classes of moduli spaces. One is appropriate for Calabi-Yau 4 folds, and the other is appropriate to other situations in algebraic geometry. Okay, let's talk give a little more detail on the basic setup. I'm going to take K of A to be a quotient group of the Grothendieck group of my category A, such that M is a disjoint union over classes alpha and K of A of M alpha being the moduli stack of objects E in A class alpha. So, for example, K of A could be the lattice of Chern characters of sheaves on some scheme X, and then this is the decomposition of the moduli stack of all sheaves into the moduli stack of sheaves of the fixed Chern character alpha. And M alpha should be open and closed in M. We suppose we're giving a biadditive map chi on this Grothendieck group called the Euler form, which is symmetric. And when we restrict our perfect complex to M alpha cross M beta, this should have rank chi of alpha beta, which is true of essentially the usual X complex and the usual Euler form, broadly. We also want a morphism of artan or higher stacks phi going from M cross M into M, which acts as the direct sum on points. This is just the kind of stacky version of direct sum in your additive category A. It's naturally associative and commutative. And in perfect complexes on M alpha cross M, beta cross M gamma, we want this identity to hold. That's going to be necessary to force the graded Jacobi identity to hold for the E bracket we're going to define. And this corresponds to kind of biadditivity of X groups, or just additive in the first factor. The symmetry property we're going to require is then going to give you additive in the second factor too. Okay, next, the multiplicative group is just C take away 0 as an algebraic group under multiplication. Point mod GM is a quotient stack where X star is just a point. So this is kind of a group in stacks, but it's not the group GM, it's the group point mod GM, BGM. So if S is an artan stack and little s is a C point in BS, there is an isotropy group of the stack S, point little s, which is an algebraic C group. And if for the moduli space, M, the isotropy group of the point E corresponding some object E, is just the automorphism group of E within the category A. There's now a natural morphism from GM into the automorphism groups, taking an element lambda to the lambda times the identity in E. So here I'm using the linear structure on the category A. And this has an incarnation in the world of stacks as an artan stack morphism psi, and from point mod GM cross M into M, mapping, well, you just mapped to E on C points, but it does something interesting on the isotropy groups of your stacks. It essentially is multiplying by lambda times the identity. So yeah, point mod GM is a group stack, and psi is essentially a group action of point mod GM, which is free except over the zero object. And this encodes natural morphisms from GM into the isotropy groups for all points E. And I need a compatibility between this group action psi and the perfect complex theta, which is usually an X complex. Roughly speaking, that if you pull back under psi across the identity of M theta, then you get theta tensored with the natural line bundle on point mod GM associated with the obvious representation of GM on C. And that corresponds to if theta is a dual of the X complex, then lambda identity of E acts by multiplication by lambda on when you stick it into the first entry in the X groups. We also need some signs satisfying these compatibility relations, and they're needed to correct certain signs in the definition of the Lie bracket or the vertex algebra structure. You can always find such signs, and if we've chosen orientations in some sense for our moduli stacks, in particular in the Calabi-Yau fourfold case, then these signs should be the natural sign comparing the orientations at a point E in M alpha, a point F in M beta, and then at their Dirac sum in M alpha plus beta. We're also going to define a shifted grading on the homology of M, such that for the substack M alpha, we shift the grading by phi of alpha alpha. So this is just the same vector space, but with the grading moved. And we're going to want that in order to make the vertex algebra structures and the algebra structures preserve the grading. Okay, so we can now give a definition of the vertex algebra structure. So, well, if we write the homology of point mod GM, this is just a point with the group GM attached to it as Q of T, where degree of T is 2. So this is, topologically, you can think about this as being CP infinity, because CP infinity is the classifying space of the group G mod M. So that's the homology of CP infinity. T is living in H2 of that. Then the state field correspondence Y of Z is given by, if U lies in M alpha and V is in homology of M beta, you get this big formula here. So what's going on is this part here, the second half of the second line lives in the homology of M alpha cross M beta. We start by taking the external tensor product of U and V. Then we cap it with some cohomology classes on M cross M, including some negative powers of Z, and a rather big exponential there. So this now lives in the cohomology of M alpha cross M beta, expanded by formal power series in Z to the minus 1. This is lying in the homology of point mod GM. So this, the entire second line, lies in the homology of point mod GM cross M cross M. So here's an extra piece involving positive powers of Z and homology classes on point mod M. Then we push this whole thing forward. Firstly, we use psi to take the homology of the point mod GM factor and the first factor of M, and then map that to M cross M. Then we use the direct sum map phi to take our M cross M into an M. We push forward this thing. This now this expression now lives in the homology of M, where M alpha plus beta, extended by formal power series in both z to the -1 and z to the +1. We multiply it by a power of z and a sign, and we're finished. Okay, so that's a horrible equation. It turns out you can prove that this does satisfy all of the vertex algebra identities. The identity of your vertex algebra is the point 1 in H0 of M0, essentially corresponding to the 0 object in your category A. It's we can also define each of the ZD like just by taking y of z from V1, or there's also a simpler definition of it. This thing essentially comes from the action of psi so it's really coming from this part. And then it then turns out to be a graded vertex algebra. So in fact, this is an example of something relatively familiar in the theory of vertex algebras. It's an example of something called a Borcherds bicharacter construction. Because a homology of M is naturally a bialgebra. It has a product from the direct sum map, has a coproduct from the diagonal map on M. The morphism psi going from point mod gm cross M into M induces a derivation of this bialgebra, making this into a commutative vertex algebra. And then there's a way of modifying commutative vertex algebras by twisting them by something called a bicharacter, which is basically coming from this perfect complex theta, to make it into a generally non-commutative vertex algebra. Okay, so we can actually give explicit formulae for these vertex algebras in quite a lot of nice cases. So there's a theorem by a former PhD student of mine, Jacob Gross. It says that if X is a complex projective curve or projective surface or a smooth toric variety, you write M for the moduli stack of objects in the derived category. And this is the semi-topological K-theory of X, which, okay, in the case in which X is the projective surface, it's the image of the K0 of the coherent sheaves, cross-linked coherent sheaves in the topological K-theory of X. Then, and in these other cases, you can also evaluate it relatively straightforwardly. Then M is the disjoint union over classes kappa in this semi-topological K-theory of X of a moduli stack M kappa, where M kappa is connected. So in fact, this semi-topological K-theory just corresponds to the set of connected components of your moduli stack M. And each component M kappa has homology. Essentially, this is a super polynomial algebra. Well, so here's a kind of an even polynomial algebra. It's getting tensor with an odd polynomial algebra. And the generators of these so the polynomials are given by a copy of the even cohomology of X here, the odd cohomology of X here. And this, it means you're taking an infinite number of copies of them. Oops. The T here is there to keep track of the grading. So basically, the T to the K part of this entire thing on the right-hand side has grading K in the HK homology group. So note that the right-hand side of this is actually independent of kappa, and that's because the M kappas are all homotopy equivalent to M0, basically. And there's a similar equation for the cohomology right here in terms of the homology downstairs instead of the cohomology. So it says we can describe the homology of M completely explicitly in the derived category case, which surprisingly is easier than the abelian category case. So nearly always derived categories are hard and abelian categories are easy, but this is a kind of thing in which things go the other way. It's rather difficult to describe the homology of the abelian category coherent sheaves on something in an explicit way. The reason for this is that the moduli stack of objects in the abelian category is essentially a monoid in stacks, because we have the direct sum operation, which gives you a notion of addition, but you don't have an inverse to that. In the derived category, you have shift by 1, which essentially acts up to homotopy as an inverse for the addition operation of direct sum. So the moduli stack of objects in the derived category is like a group in stacks, whereas the moduli of objects in the abelian category is like a monoid in stacks, and really groups are kind of simple objects and monoids. We can also describe the homology of moduli stack explicitly if M is a quiver moduli stack, and in some other cases. Okay, so a way I like to do this is, let's work in the situation of theorem 1. Let's write U kappa for the universal complex over the product of X and the moduli space M kappa. BK are my Betti numbers. Let's choose some bases for our rational homology, EJK. Epsilon JK are the dual bases of the rational cohomology. And then for L greater than the K over 2, I define big SJKL in the cohomology of M kappa to be the nth Chern character of the universal complex is slash product with the homology element EJK. So this I think of as having degree 2L minus K and as being an even or odd variable if K is even or odd. Then the cohomology version of theorem 1 says that the cohomology of M kappa is exactly the super polynomial algebra generated by these variables, even or odd variables, for variables in these ranges. And note that L is an integer which can be as large as you like, so there are infinitely many variables here. It's an infinite dimensional, it's an infinite dimensional and infinitely generated polynomial algebra. It's a dual description of homology with little sjkl variables, which are kind of dual to the big sjkl variables. I also add in a formal symbol each of the kappa to remember what my kappa is. Its degree is that thing to get the correct shifted degree. And here's the pairing between cohomology and homology. I put in these slightly funny products of factorials because that gives nice algebraic properties later. So this now gives us a completely explicit identification of the homology of our moduli stack M as a direct sum of kind of group ring part in each of the kappa, and then a super polynomial algebra part generated by infinitely many even and odd variables. Then in these coordinates, the vertex algebra can be written in this, like this huge great big equation. So I'm thinking about it in terms of differential operators acting on my polynomials. So elements of my homology, I'm thinking about them as kind of formal functions in these variables, and then my state field correspondence is acting by all these formal differential operators. And it's quite complicated. So here I'm using this NJK matrix. This is a matrix of the symmetrized Mukai pairing. So the Mukai pairing is the pairing on cohomology you get by integrating one cohomology basis element cut with another cohomology basis element cut with the Todd class of X. This depends upon the X as a complex manifold. So N is a kind of symmetrized version of this. This corresponds to the symmetrization of the X complex, which I was doing to define my complex theta. What we do is, we take our, I'm going to take two different copies of my variables sjkl. So sjkl and s prime jkls. Inside the brackets, I have two different copies of my variables on the go. So I take the u thing in the s variables, the v thing in the s prime variables. First, I apply an exponential of a sum of d2 by dsj, d2 by ds primed j. So the first thing is acting on the u, the second thing is acting on the v, times this matrix, times the factorial, times the power of z. So after I've applied that exponentiated operator, then I apply this exponentiated operator, which acts just on the s prime variables, so just on the u part Then after that, I set S prime variables as S variables. So this corresponds to pushing forward along the direct sum morphism, multiplied by a power of Z and by a sign, and I'm finished. So, okay, this is, I've hidden some complexity in this. So I have these e to the alphas and e to the betas. My differential operators also have to act upon the e to the alpha and e to the beta terms. We do this by introducing extra variables, Sj, k over 2, such that alpha can be written that way and beta can be that way. So e to the alpha, really hidden in here, there are some extra exponentiated sjk variables, so that the effect of taking derivatives by these things is to multiply this by alpha jk. Okay, so this homology, it's a variant of something called a super lattice vertex algebra. And this equation is really horribly complicated to do any explicit calculations with, which is what's been making my life miserable for about the last 3 years, is that you have to deal with all these exponentiated operators one after the other. Okay, so 3 postdocs, Arcadio Boyko, Winam Lim, and Miguel Moreira, did some rather nice work in 2022. If you suppose that X is a projective surface with B1 as 0 and H2 0 as 0, then if nu is the inverse matrix of this symmetrized mu chi pairing N, you can define an element omega in H lower 4, the fourth homology group of M0, by this explicit formula. It then turns out that omega is a conformal element for this graded vertex algebra X star of M, makes it into a vertex operator algebra. Okay, I can also make the homology into a vertex operator algebra without assuming B1 is 0 and H2 is 0, 0. But then you have to use a Hodge decomposition, so you have to work over the complex homology into HPQ things. You have to modify your vertex algebra by adding some finitely many extra variables X, Sj, PQL, and then you, instead of shifting just by the degree here, you have to shift by the kind of pth, the P and the PQ in the Hodge groups. And if you take M to be the moduli of objects in the abelian category of coherent sheaves, this is not a vertex algebra, vertex operator algebra, because the conformal element has to live in H4 of M0, but in the abelian category case, the only object in class 0 is the 0 sheaf. So M0 is just a point, and it's H4 is 0, so there is nowhere to put a conformal element. And this story about conformal elements and vertex operator algebras has some quite nice applications to Newton invariance of projective surfaces. It turns out that the Virasoro algebra derived from this thing satisfies some identities with respect to Newton invariance counting coherent sheaves on projective surfaces, which fits into a story relating the Virasoro constraints on Gromov-Witten invariance and various parts of string theory. Okay, next let me tell you how to make Lie algebras on the homology of some slightly different moduli spaces. So by a construction of Richard Borcherds, because the homology of M with this shift is a graded vertex algebra, then you can take the quotient of the homology of M with a shift by 2 by d of this thing, where d is this translation operator. This gives you a graded Lie algebra, where this is a translation operator, and it has a super Lie bracket, just taking u0 v mod d, really. So I bet something rather nice in the setting we're talking about is that this has a geometrical interpretation. So point mod gm is a group stack. Psi is an action of this point mod gm cross m into m, is an action of this, which is free except over 0. And you can form a quotient stack, MPL, dividing out by this, which is called the projective linear moduli stack, with a morphism from M to there, which is a principal point mod GM bundle, except over 0. So the C points of MPL, they're just isomorphism classes of objects in A, but the isotropy groups are the quotients of the automorphism group by the multiples identity. We're making this projective linear moduli stack from M by quotienting out all the multiples identity from the isotropy groups. That's something fairly well known in algebraic geometry. It's a process called rigidification. And there's reasons to care about it. In particular, if you have a moduli scheme of stable sheaves, then that moduli scheme is actually an open substack of this projective linear thing. Because a stable sheaf always has automorphism group GM, so factoring out by it actually turns your stack into a scheme. And there's many reasons to care about moduli schemes of stable objects. And this projective linear moduli stack is a way of comparing moduli schemes of stable objects for different stability conditions by including them all into the same single larger object. Okay, so it turns out that the projection from the homology of M to the homology of MPL, it has this D of H star of M in its kernel. So it descends to a projection from this quotient, which is the Lie algebra, into the homology of this projective linear moduli stack, which is an isomorphism. Well, okay, I've missed out an assumption here, but never mind. In nice cases, at least, it's an isomorphism for all alpha in your K of A except alpha equals 0. So let's write H hat star of this with a shifted grading, as we did before. Then it turns out there is a graded Lie bracket on this shifted version of the homology of MPL, defined using something called the projective Euler class. So incidentally, Markus Zuckmayer is a good person to talk to about all this stuff, if you want to, because he worked out some part of this Lie algebra story when he was working with me in Oxford. And you can see a paper by him in 2021. So then this projection is a Lie algebra morphism from this thing, which is really just an algebraic thing, to this thing which has a geometrical meaning. And it's an isomorphism except over the stack containing the component containing 0. So this Lie bracket on this homology of the moduli stack is very important for the theory of unit invariance. We can also give an explicit formula for this Lie bracket if we restrict to sheaves of positive rank. So let's write M rank greater than 0 for the substacks of sheaves and complexes with positive rank. Then you get a surjective morphism from the homology of the rank 0 moduli stack to the homology of the projective linear rank 0 moduli stack. If we suppose that X is connected, this induces an isomorphism from the kernel of what S101. It's a kind of first cohomology variable, if you like, in H2 of this moduli stack, corresponding to the first Chern class of your universal complex and essentially the class of the point in X. So this gives you an isomorphism. This is naturally a quotient of that vector space. You can also identify it though with a vector subspace of this, meaning the kernel of this thing. And this, if we in our kind of polynomial superalgebra, this kernel is just the functions independent of the homology variable S101. So therefore, you can identify the homology of the positive rank projective linear moduli stack as this direct sum of some grouping elements times a polynomial superalgebra, where now I'm excluding JKL as 101 to make these independent of the homology variable S101. And then with that identification, the Lie bracket on this homology can be written like this, involving, okay, so Again, there's kind of exponentiated operators involving the symmetrized Mukai pairing, and now there's two of these things instead of one. And we have to take a residue of, so this thing inside the brackets is a great big formal power series in Z. We take the residue, meaning we take the coefficient of Z to the -1, and that gives us our Lie bracket. And again, this is monstrously complicated to do explicit calculations with, but that is what I've been doing for the last few years in studying invariance of projective surfaces. Okay, so a few remarks. Well, so firstly, this theorem, which gives you an explicit description of the homology of your moduli stack of objects in the derived category. It only applies to certain special smooth projective variety of X, curves, surfaces, target varieties, or Grassmannians, and maybe a few other cases. But actually, for all smooth projective X, and for M, the moduli of objects in either the abelian category or the derived category coherent sheaves, there is a natural vertex algebra morphism from the homology of the moduli stack M, which is unknown, to this explicit vertex algebra in these variable e to the capital S JKL, and similarly for the positive rank, the algebra, and the explicit Lie algebra as we've written down. So my kind of general approach to these things is, well, if you can't write this down explicitly, you just project to the explicit thing you can write down and work there. There's also similar explicit formulas for vertex algebras and Lie algebras coming from moduli stack of objects in quivers or their derived categories. Actually, so we can make this case explicit, even though it's an abelian category. The derived category yields a lattice vertex algebra. The graded degree 0 part of this graded Lie algebra here for the derived category, the quiver, is exactly the Kac-Moody algebra associated to the underlying undirected graph of the quiver Q, considered as a Dinkin diagram. So, for example, if Q is an ADE quiver, you actually get a finite-dimensional ADE Lie algebra. So this is a rather nice thing. There's all kinds of constructions in representation theory where you start with an ADE quiver or a Kac-Moody quiver, and you do something, and usually people can manage to spit. Usually people kind of start with the abelian category, and then they spit out something to do with the positive part of your Lie algebra. And then you kind of feel that, well, you ought to be able to do some kind of doubling construction and start with the derived category and end up with a full Lie algebra or something associated to that, and it usually doesn't work. But here's in a case in which it does work. Starting from the abelian category gives you the positive part of your Lie algebra. Starting from the derived category gives you the full Lie algebra, and it's just a single construction. Okay, so here's what I'm really interested in. So in Newton invariance. So in Newton invariant theory in algebraic geometry, it's a study of some invariants counting semi-stable objects E with some fixed topological invariants. Here, Tor is my notion of stability. Usually in some geometric problem, usually by means of you take a virtual class for your moduli space of semi-stable objects. So this is a homology class in some homology theory. And then your invariant, you take your virtual class and then you integrate against it some natural cohomology classes mu alpha in the problem, and you get a number or some element in some ring or something like that. And we call this theory C-linear if the objects E live in a C-linear additive category A, such as coherent sheaves on something. So, for example, you could look at invariants which count semi-stable vector bundles on algebraic curves. You could look at invariants counting coherent sheaves on surfaces. There's a monograph by Takuro Mochizuki on these. You should think about these as being some kind of algebraic Donaldson invariants of the underlying four manifolds. Donaldson-Thomas invariants of Calabi-Yau threefolds or of Fano threefolds. Donaldson-Thomas type invariants of Calabi-Yau fourfolds, and invariants counting representations of quivers or quivers with superpotential. So all of these are going to fit into the general framework I'm going to talk about. So in this rather long paper, it's about 300 pages long, I proved that many such theories in algebraic geometry, basically including the entire list I just gave you, in which either the moduli spaces are automatically smooth, such as coherent sheaves on curves or quiver representations, or else the invariants are defined using Baron-Fantacci obstruction theories and virtual classes. These theories share a common universal structure. So I would define the invariants to be homology classes in the homology of the projective linear moduli stack. So the reason that's a good idea is that if stable equals semi-stable, then the usual moduli schemes, which algebraic geometers tend to consider, are actually proper open substacks of this projective linear moduli stack. So their homology classes initially lie in the homology of the moduli scheme itself. They just push forward to here. And if Tor and Tor twiddle are two different stability conditions, and alpha is some K-theory class, there is a universal wall-crossing formula of this form, where these U-twiddle things, they're rational numbers, combinatorial coefficients, which actually go back to my previous work on wall-crossing formulae for motivic invariants. So this is something which, a formula of this shape with the same constants U holds in lots and lots of different theories. For sheaves on curves, sheaves on surfaces, quiver representations, all of them. The difference is the Lie bracket. So we're now going to use the Lie bracket on this homology of the moduli stack, which I've explained. And in fact, this wall-crossing formula, there are various previous incarnations of it for motivic invariants, where the invariants are not defining the homogeneous classes, but using some kind of numbers. So there's a previous version of this wall-crossing formula in which the Lie brackets are happening in a Ringel-Hall algebra of some kind, or some fairly explicit Lie algebra, rather than in a Lie algebra constructed on homology. Anyway, and as we've seen, the expression for the Lie bracket on the homology of the moduli stack is really a very complicated thing. It involves all these exponentiated differential operators. So it's really non-trivial, this Lie bracket, in order to make this wall-crossing formula hold. And so how I came to invent the vertex algebra and Lie algebra structures I'm talking about was in order to be able to write down this wall-crossing formula. And, well, it turned out to be more complicated than I bargained for. So vertex operator algebras also get involved in the Virasoro constraints on the invariants. So it turns out that in some problems, these counting invariants satisfy natural identities induced by the Virasoro algebra, and that's something which these postdocs Boyko, Lim, and Morera discovered in 2021. And so that's nice because it's something in which the overlying vertex operator algebra actually gets involved in some interesting way, rather than simply defining for you a Lie algebra. Okay, also got a few more minutes left, so let me talk about generalizations of this construction. It turns out that there's lots of kind of bells and whistles you can change in this construction. So let me run through a few of them. To get an ordinary vertex algebra, I assumed that this complex theta had a symmetry property, that if you swap round the factors of m, then that turns the complex theta into its dual with an even shift. And to get this, if m is the moduli of objects in cox or dB of x, you need to assume that x is either an even Calabi-Yau manifold, and then you take theta to be the dual of the x complex, or else you just symmetrize theta in this way. You symmetrize the x complex in that way. and then so this becomes trivial. If instead you just take theta to be the dual of the x complex, if x is not even Calabi-Yau, you get a different kind of vertex algebra, something called a non-local vertex algebra, or a quantum vertex algebra. And this basically corresponds to it's a vertex algebra version of a non-commutative algebra rather than commutative algebra, because it's this thing is corresponding to the commutativity property of your underlying algebra in a sense. And quantum vertex algebras have various applications, and some of the things you can do with vertex algebras still work. Next, we can talk about equivariant homology. Oops. So if we let an algebraic C group act on category A, so that G acts on M and MPL, then for a slightly unusual notion of equivariant homology, I can extend the vertex algebra and Lie algebra theory to the equivariant versions. And this is also the right context to extend the Newton invariant program to invariance in equivariant homology. So here, what you might guess is that the appropriate definition of equivariant homology of a stack X is you just divide X by G and then take the homology of that out on stack. Instead, my equivariant homology is defined for K in the integers, not K non-negative. And if G acts trivially on X, then the equivariant homology of X is just a tensor product of the homology of X and the cohomology of point mod G. But the cohomology appears with negative grading. So really this is an H, kind of H to the minus J of point mod G, which is why you need to grade over the integers and not over the natural numbers. Secondly, what I've told you about today is essentially a kind of even Calabi-Yau construction. I actually discovered it when thinking about how Wall-Crossing formally worked for Calabi-Yau fourfold counting invariance. Now, there's also an odd Calabi-Yau version of this. It gives you something called a vertex Lie algebra. This is a weakening of vertex algebras which only remember the poles in your state field correspondence, so the negative powers of Z. And if you start with an odd Calabi-Yau category, or so you assume your theta has this symmetry, but now with the shift 2n plus 1 instead of 2n, then there's a way to define a graded vertex Lie algebra thing. So this looks exactly rather different to the previous thing because there's no exponentials. Things we had before, there was an exponential of the Chern characters going on there, but now it's just some kind of sum with some factorials in it. Okay, and this also spits out a graded Lie algebra structure on the homology of the projective linear thing, but now with a slightly different shift. I expect this to have interesting applications to equivariant Donaldson-Tomlinson variants, counting compactly supported coherent sheaves on a local Calabi-Yau threefold. There are notions of complex-oriented generalized cohomology theory. This is a generalized cohomology theory with a notion of Chern class. Examples include the ordinary cohomology theories, but also K-theory, elliptic cohomology, and unitary Borcherds and cobordism. So any complex-oriented generalized cohomology theory over some ring R has an associated formal group law F over R, where ordinary cohomology is associated with the formal group law S plus T, called the additive group law. K-theory corresponds to a different formal group law S plus T plus ST. So it turns out that there is a notion of a vertex algebra over a formal group law, F, where ordinary vertex algebras in classical sense are just vertex algebras over the additive formal group law. So if you suppose you have some complex-oriented generalized cohomology theories of R-term stacks or higher stacks, written as E star, associated with formal group law F, then my construction generalizes to give you a vertex algebra over the formal group law F on E star of M. And again, this is something which Marcus has been involved in. He's got a rather nice paper with Jacob Gross about it from 2021, working out this story. And finally, there's something you can do for self-dual categories. suppose you've got an additive category such as vector bundles on X or derived or perfect complexes, and you have an equivalence of the category with its opposite. For example, this could just be gradient duality, or you take a vector bundle to its dual. Then you can look at self-dual objects. The fixed points of this delta, they're something like a vector bundle with nice morphism with its dual. So basically vector bundles with orthogonal or symplectic structures. So my student changing Bu shows that you can give this moduli stack the structure of a module over the vertex algebra we've already defined, and it also gets a representation of the graded Lie algebra, or the -1 eigen subspace, -1 eigenspace of delta in the vertex Lie algebra. And this turns out to be important in the study of enumerative invariance counting self-dual objects. For example, if you would like to count principal ONC bundles or principal SP2NC bundles on projective surfaces. Okay, thank you. That's all I've got to say. I'm still going. So, do we have any questions?
Questions for the speaker?
Yes. You constructed new examples of vertex operator algebras. So first question, are they isomorphic to known examples of vertex operator algebra? And second thing is that in many cases, the category of representations of a VOA is monoidal. Does that happen in the examples that you construct?
Well, so whenever I can actually compute a vertex algebra coming out of this construction, it's basically some variation on the lattice vertex algebra. So in that sense, it's not really coming up with interesting new stuff from the point of view of the people that study vertex algebras. And as some monoidal things, well, I haven't got that yet. So you're talking about, you're interested in some form of tensor product of representations of vertex algebras, are you? Yeah, so I haven't got anything useful to say about that, I don't think. And so there's kind of geometric constructions of representations of vertex algebras. I mentioned one in the last slide. Yeah, and I think this picture is sort of more useful for starting to think about vertex algebras and things like that associated to semi-stable moduli spaces in the kind of Gronowski-Nakajima type sense. And maybe the kind of thing that some string theorists would like to do, like Fagin and Gupov. I think this is a good starting point for understanding those things, but you need some modifications to be able to associate vertex algebras to semi-stable moduli spaces instead of the full moduli space.
Another question?
Yeah, so Udi asked almost the identical questions to the one I had, but now I have a follow-up question. So since a lot of the flavor that you get is lattice algebras, the representation theory is very right. So do you think that the representation theory has any implications? Because you said you found a few at the end, representations. I mean, right, so going representations is already like an order problem that comes further down the road, but just like any relevance of the representation theory, the problems.
Well, as I said, what I'm mostly caring about is enumerative invariance. And there's a lot of suggestions that the representation of the vertex algebras should get involved in understanding these. So, for example, there's the work of Gronowski and Nakajima, which says that you take the homology of Hilbert points on a Hilbert schemes of points on a surface, you can make those into a vertex algebra. And their generating functions tend to be modular and things like that. And yeah, for a lot of stuff to do with projective surfaces, you can make modular functions come out of it. And I believe that should be associated to a representation of the vertex algebra story, but not quite the vertex algebras I've told you about. But instead, those vertex algebras ought to be built out of essentially the vertex algebra associated dimension 0 sheaves, which I've told you about, acting on moduli spaces of semi-stable sheaves. So what I've told you about, in some sense, those vertex algebras are too boring. Although you can get interesting sub-algebras of lattice vertex algebras by using screening operators and that kind of thing. And there may be some kind of geometric way of doing that. But yeah, okay. So I think that there is a lot of interesting vertex algebra stuff to do here, but not exactly starting from what I've told you.
Thank you.
Any further questions? Maybe I have one more, but it's not a real question. So you mentioned that vertex algebras appear in physics, of course, as do some of these enumerative problems, like, I don't know, counting sheaves and so on. So have these structures appeared in string theory? So have you asked people about this?
Yeah, well, and so there's a paper by Feigin and Gukov, who are basically string theorists, called VOA M4. So they're conjecturing that to any four manifolds, you can associate a vertex operator algebra, which has a representation on the homology of all the moduli spaces of sheaves, let's say with a fixed rank R and semi-stable. Well, roughly, they probably say they wanted to act upon the homology moduli stacks of Varpel-Witten solutions, but to some approximation, that's acting on homology of moduli stacks of semi-stable coherent sheaves on your projective surface with a fixed rank R. And my Newton invariant theory produces homology classes in the homology of the projective linear moduli stack. To get the vector spaces associated to that, you should start with that homology class, take the cat product of it with all cohomology classes in the cohomology of the moduli stack. That gives you a vector subspace of these homology of projective linear moduli stacks I've been talking about, which is a substitute for the homology of the semi-stable moduli stack. And I'm expecting that the Feigin-Gukov vertex operator algebras, the representations they tell you they want, act exactly on the direct sums of these vector subspaces of the homology of the projective linear moduli stack. So I basically like the Feigin-Gukov VOAs to act upon the entire homology of the projective linear moduli stack and preserve a vector subspace which comes from semi-stables. And then that kind of thing would, representation theory of vertex algebras would serve to explain modularity properties of things like the chi-y genera of homologies of moduli spaces of sheaves on projective surfaces and that sort of thing. So that's one story I'm particularly interested in.
Thanks. All right. Seeing as there are no further questions, let's thank Dominic again.